Okay, so we're going to talk about covalent networks. Covalent networks are very similar to the crystal lattice structures that we see with ionic compounds. So with an ionic compound, you're going to have that crystal lattice where it's positive, negative, and it's a very ordered and strong structure, which makes the melting point of ionic compounds very high because you have this crystal lattice structure. Now, some elements are able to create a network that's similar to this, and the fact that they have an element connected to another atom, and then it just goes on and on and on. And this essentially happens a lot with group 14, with silicon and carbon, because they're able to make those 4 covalent bonds. But because they can just continuously bond to another atom, it creates a very strong network. Okay, so these large continuous networks are very, very strong. So silicon and carbon do this a lot because, like I said, they can make those 4 covalent bonds. So with carbon, there's a lot of different allotropes, and an allotrope is where you've got the same substance making up that compound, but it's completely different structure. So that would be like diamonds and graphite, and then there's charcoal. Now, these bonds, because of this network and the fact that the bonds are strong, the melting point and the boiling points are going to be very high. Now, a lot of these networks are very poor conductors of electricity because the electrons cannot move around. There is an exception, though, with graphite. Graphite will conduct electricity because there are delocalized electrons because of the way that the network is structured. Okay, so let's look at diamonds versus graphite. So with a diamond structure, we're going to get these 4 covalent bonds. So we have essentially each little piece is a tetrahedral shape, but they just keep attaching to more and more of these structures, which makes it very strong. Graphite has actually got 3 connections. So the carbon atom right here is connected to 1, 2, 3 other atoms. Since it's only got those 3 covalent bonds, what ends up happening is there's a free electron right there. So right between these 2 layers, we've actually got free electrons that move around, which is why graphite can actually conduct electricity. So with a diamond, we're going to get that tetrahedral unit, and then you're going to get very, very rigid angles, very, very strong bonds. Now, with graphite, it only bonds with the 3 other carbons, and then you're going to get a free electron because of that. So those free mobile electrons are kind of moving around between the layers, okay? And the layers are held together because of these weak LDFs, or the London dispersion forces that hold the planes together, which means that graphite is very soft. When you compare graphite to a diamond, diamonds are very, very hard. Graphite is not. So with carbon networks, we're going to have these carbon-carbon bonds, and these are going to be stronger because the bond strength between a carbon and carbon atom is stronger. The silicon, of course, will contain silicon to silicon bonds. Now, silicon is a poor semiconductor. It's a metalloid, okay? It can conduct electricity, but to a very, very small extent. But you can actually take a silicon network and dope it to make the conductivity go up. So you can add an impurity to it, and then that impurity can help increase the conductivity. So what you can do is you can take something that's got 1 more or 1 less valence electron than silicon, so something from group 13 or something from group 15, you put that inside the network, and then that disrupts the electrons and the valence shell of the silicon. And then that's able to create more delocalized electrons. And then you can also increase the conductivity by heating it. Now we also have something that can, like a molecular solid. So a lot of covalent compounds, if you look at the halogens, a lot of those are going to be gaseous, but iodine is actually usually found as a solid. It's a molecular solid, okay? So you can have these solids that form from molecules that are covalent. Now, it's similar to in the crystal lattice that you see in ionic compounds, that it makes that very ordered structure. But the melting point is going to be much lower compared to an ionic compound, because the thing that's holding this molecule to this molecule is going to be a London dispersion force, or an intermolecular force. So it's a weaker attraction. And also, with these molecular solids, you will not see any conductivity of electricity whatsoever. Okay, so something that they could do is they could give you information about the compounds and then ask you to kind of determine what type of bond you think might be present. The first thing you want to look at is going to be your conductivity. Now, if you see that it conducts electricity as a solid, automatically, one of the things that you couldn't think of is, well, that could be a metallic bond. And if you have graphite, graphite will conduct electricity, but then we go back and we're going to look at the melting points. And graphite's melting point is not going to be quite this high. So this has a high melting point. It does conduct electricity as a solid. It's probably going to be a metallic bond. Now, let's look at the other options that they give us. So for option C, it's not a good conductor as a solid. It's not a good conductor as a liquid. And the melting point is very low. So for this one, I would say that this is a molecular solid. This is something that we've got intermolecular forces holding it together because that melting point is too low. Now, then you have 400. Okay, so it does not conduct electricity as a solid. Okay, but it does conduct electricity as a liquid. That right off the bat should tell me that that's an ionic compound, because as a solid, those ions are not able to move around. But if you melt it, or if you dissolve it into water, the ions can now move, and then that's when you can get your conductivity. So this one should be ionic. This one's probably a metallic bond, and then this one's probably a molecular solid.